Our next presenter is Chris Morin. Chris has been involved in forecasting in the Pacific Northwest for over 10 years. He's a pro patroller at Crystal, and he runs a company called Storm, and they do machine learning data forecasting. I probably just mangled that because I'm totally above my pay grade. But he's here to talk about bridging the gap between big data and the Avalanche practitioner.
Thanks. So actually, am I here? So actually I don't pro patrol at Crystal anymore. I stopped 4 years ago. I worked there for 7 years. I was assistant snow safety there. I do some other forecasting for the railroad still. But 4 years ago, I started working at Eddie Bauer running their analytics, and I've really been trying to merge the two fields. It's been data science in the Avalanche field can be a tough sell. Usually you're up here after a bunch of drone footage of avalanches, and you have some charts where the lines are close together, and it doesn't always capture people's interest the same way. And I saw the ISSW a few weeks ago, which is similar to this. It's a more technical version of this presentation, and the practitioners weren't really seeing the benefit of some of the science being presented, although it has a lot of the same corollaries to what they were looking at day to day. And my work is really focused on making that work actionable, making all the science, all the data we have today useful in people's day-to-day work, and specifically looking at it from a weather standpoint. So just to go over the current state of weather forecasting, I don't think everyone understands exactly how the weather forecast is manifested every day. In the past, in general, they looked at the entire weather forecast, a bunch of stations, it's Mark Moore looking out the window 30 years ago, writing down a piece of paper, mailing it to somebody, and that's your weather forecast. No computer input whatsoever. Some of this stuff, I would call it borderline witchcraft in how they were doing it. I mean, how would you forecast weather 50 years ago? It was extremely tough. Today, it's a lot more confined to using big weather models that give you a bunch of parameters. They almost give you the answer to some degree. You look at the current state of the atmosphere, you input all this information, and they spit out an answer, their point of view on what the weather forecast is going to be. And the forecaster comes in of looking at all these different models. There's names for them. You get the GFS or the high res, and it compares the differences between them. He looks at differences in the general atmospheric layers and tries to come up with a forecast based off of these. So they don't complete the process. So what is a numerical weather model? You're using mathematical models to run on large computing clusters to make a forecast. This is a map of weather stations across the globe. So if you can imagine, you're looking at west-east wind pushing systems in across the west coast. That iterates it, steps it over time, and tells you what's going to happen in 1 hour, 2 hours, 3 hours, 4 hours. So a bunch of math happens. They're really complicated. We're not really going to get into that piece of it. But end result is you get a bunch of numbers out of these models. I simplified a few steps there, but I think it's appropriate for the crowd. Some of what I do is up here. A lot of what I do is down here. So what do you do with this? Some of this option, you can map it. That's the current GFS output. I think this is mostly what people think of when they think of weather models. You can see there's a low spinning off the coast here, pushing some weather into us. It's a little ridgier and drier in the Midwest here. And when I say you can see that, if you forecast weather often, that's immediately apparent to you. But I think a lot of recreational users can't translate that into actually what's going to happen today, tomorrow. What's that mean for traveling in avalanche terrain? So it's a bit abstract for a recreational user. You can also do a point forecast, where you basically take a single point out of this model and just dump what it says without filtering too much. So this is the forecast for Baker today, actually. I'm busted with when I actually put my presentation together because it's current. It says Sunday, 30% chance of showers, mostly cloudy. Basically, it's telling you it may or may not rain. There'll be some clouds and also some sun. So they nailed it. I don't know who put that out, but solid work. So what are the limitations to this? You need highly trained meteorologists at Avalanche centers to interpret this model output. There's a few people here who probably looked at it, but it's not simple to look at all these models and understand which one to go with and how to give a avalanche forecast based off of it. I don't think we realize how fortunate we are in the Northwest to have the forecasters we do. Most avalanche centers don't have highly trained meteorologists, or they only have a few. So we're really in a unique situation. A lot of places just have volunteers. There may really be no weather forecast whatsoever. So this is a big pinch point for a lot of organizations. They're also forecasting very large areas. So you're looking at all this stuff, but if you want very high-res forecasts right where you're at, it can be hard to give you hourly winds. You know, I'd call them all the time working at Crystal, 6 times a day, trying to figure out, well, is it going to be windy in the next 30 minutes? An hour later, I'd call them again, ask them if it's going to be windy in the next 30 minutes. And they don't have the bandwidth to necessarily give as much information as the public can consume. And like I saw, the direct model output, you can't look at all these models, but it's a varying usefulness and accuracy for a recreational user. And it's also not where your time should be spent. If you spend a lot of brain power looking at all this model output and trying to create a forecast for yourself, it distracts from the much more complicated problems, which is really the avalanche problem itself and decision making and all the rest. So it's not something that's functional right now for a recreational user to go directly to the weather models and get output efficiently. So how can we improve this? We can make the raw output better. So if the models were perfect, we'd be good to go. You just pull out the forecast from them. You make them higher resolution. You can change them to physics specific to your forecast area. These models are forecasting for the whole globe. They're trying to figure out what's going on in India. Well, what if we just made them specific to the Cascades? Because you parameterize them better to get better output. And you can do that. You can run what's called a WRF model. It's an open source model developed by NCAR. It's very powerful. But why do they not do this? Well, it's cost and complexity. You have to build a cluster up because it takes a lot of processing power. So you have to have 48 cores. You have to have a Linux administrator to do that. You have to batch it. It's not a simple thing to do. Colorado is actually the only place that does this currently. They have a cluster sitting in some guy's closet. He happens to be a PhD in meteorology. He's done this his whole life. So they're in a unique situation, but it's very hard to scale that. So how can we solve these barriers? A solution would be cloud computing, right? You don't have to build up this hardware in your closet. You can spin up clusters in the cloud. And this has been one of the big unlocks to being able to develop this work for smaller organizations, is I can spin up a cluster as big as you want in seconds in the cloud. You can get 128 cores on your Linux cluster in 30 seconds. You just hit the button. There's no upfront cost. It's efficient. It's scalable, meaning you can pound out a WRF over Washington State. You can also scale it to the whole West Coast if you want. It's a very efficient, quick way to do it for very small organizations. You pay hourly. So when I spin this stuff up, I pay per hour the thing's on, and I turn it off when the model's done. So we're doing this. So here's the GFS output from, I think this is yesterday, midday, and it's temperature. So you see the red areas are warm, blue areas are cooler. These lines are the freezing levels. So GFS is telling you that it's going to be colder near the top of the mountains at the Olympics and warmer lower down, which helps you to some degree, but doesn't have near the resolution we would need to actually start forecasting pinpoint avalanche weather. So this is the WRF that same time period. So you can see there's a big difference in resolution. You can start pulling a ton more detail. And this gives you much better forecasts. It's a lot better resolution, a lot better forecasts. You can also pull out the raw data, so you're not looking at 500 millibar charts. You're looking at something that may be more applicable to your day-to-day user. But there's some cons. You can only do so much with a WRF model. You can keep going higher and higher and higher resolutions. If you start getting diminishing returns, you also start getting bad data the lower you go. You can't do a 100 by 100 meter grid without spending a ton of time on it. And it's still not good enough. I can look at the data coming out, and we did run this a bit at Crystal last year, and they used it operationally, and they found it super useful. They said it was super accurate, but I look at the raw numbers. There's some big misses still, especially around Baker, some of the convergences around Stevens. I say it's not good enough to necessarily take those raw numbers, throw them out, and have that be your endpoint. So another step with this, you run this big weather model in the cloud and use machine learning. So currently, we're producing over 100,000 values a second, 24 hours a day, from this weather model output. So it's a torrent of data, and we're only looking at little pieces of it. You can use all of this raw output by machines to learn how to forecast similar to the way a human forecaster would learn. So if you think about the way a human learns to forecast, there's a lot of pattern recognition. They've seen this pattern in the past. They know this model works better in this specific case, or it over-forecasts or under-forecasts in a specific case, and they create forecasts based off that. You can train machines to do the same thing, similar to how they've learned to identify your face on Facebook, because they've seen a lot of pictures where you've been tagged, and they know that's you, and then they can apply that to new images. So you can apply the same technology to weather forecasting. And I think it's interesting because we're doing it here. I haven't met or talked to anyone that's doing that at the same scale, so it's a bit of a new field. And we're getting some really promising results out of it. So you basically take stacks of temperature, wind, precipitation, all these dimensions, right? Same as you would if you were a forecaster. The machine looks at them, compares them to what was happening at the weather station at the time, and says, oh, I thought it was going to rain an inch. It really rained at 0.9 of an inch. I learned from that based on all these variables. Kind of makes sense from a very broad scope? We'll go with yes. Yes. So does it work? And I'm always really focused on what are the results. I don't care how you get there. People have opinions on what algorithms you use or what your physics are or what your step size is. I really just want to know, well, how close can you get to what's actually happening? And you can look at a lot of statistics with this stuff, but I think it's more meaningful to look at the raw data and then translate, well, what does that mean to your day? So this is running 4 times a day right now. It's been running since Wednesday, I think it's been live. We've been doing the work for years, but this is the output for the top of crystal and the bottom of crystal temperature since, I think this is Wednesday down here. So orange is the model output, and blue is the actual temperature. Again, this is mountaintop at Crystal Mountain, and this is the base area at Crystal Mountain over the last 72 hours. And this gap right here, just for scale, is about 1.5 degrees. So up top, you can't read that at all, but the average difference between the model and the output here is about 1.7 degrees. 95% of the forecasts were within 3.7 degrees of the measured value. So 95% of the time, we're within 1,000 foot of the freezing level hourly. So that's a really promising output. And down here, it's a little better. I think it's 1.5 is the average difference. So means on average, you're within 1.5 degree of that sensor. 95% of the time, you're within 500 feet or so of that sensor. I wouldn't say these are always reproducible. I literally just took the one area and just plotted them up just to see where we're at. But there's a ton of promise in some of this work. Here's like precipitation at Crystal. We had a bit of a rain event October 20th. It was like Friday-ish. Forecasters. Mark, did it rain on Friday? Yes. Mark said, yeah. Mark, perfect. So I got, again, it's hard to read, but the actual was about 1.3 inches of water. I got 1.7 inches of water. And this is the hourly water SWE. So it's not perfect, but that's pretty good for a completely automated system, right? No human intervention whatsoever. So what would this look like if you were to scale it? So what we've done is we have a WRF model running in the cloud. We've done a bunch of machine learning off this WRF model, and every single sensor that NWAC has, I've created a model for it. Essentially, you have a computer forecaster for every sensor, for every station in Washington State. So you end up with, you have like 140 or so sensors. It's a pretty wide body of work, and I'm going to talk to you later about, there's some limitations with that. You can't police all this stuff because you're producing like 10,000 hourly forecasts 4 times a day for each of these. So it's not something that you could filter, but let's see what it would look like. And I had Libby back there just go to the live demo. Can you do that? So I was on Instagram on Wednesday, and I saw a post that NSAW was in 4 days, which is the first time I realized NSAW was this weekend and not next weekend. So in the last 4 days, I built an interface just to have something for people to interact with. So it's definitely still pretty basic, but I think it gives a general idea of what's possible, like what you could do with this data. So up top, it's going to be tough to read. It's at winterscience.com, so you can just go to it. It's live. It's running 4 times a day. Stuff's updating constantly. All the NOAC telemetry is coming in every hour. So up top, it looks at the last 12, 24, 48, 72 hours of water content. So not a lot going on at Crystal. Below that, that's the forecast. The next 12 hours, you get a 100th. 24 hours, a quarter. The next 48 hours, a half. It's like 6/10 in 72 hours. So you have the actuals, forecast. These are just current temps. NOAC has some really cool charting going on. I just threw something out. So here's temperature at Crystal. There's a mountaintop and base temperature chart. This line right here is the freezing level, and there's water down here. So you can see, it looks like rain. I can't read that, but rain in like 23 hours or so, followed by maybe some snow at mountaintop, because we're starting to dip below freezing at mountaintop for the next 48, 72 hours. In the gray is actual. This is what actually happened. This is mountaintop wind. Wind is phenomenally hard to forecast in some of these spots, so you spent a lot of time on that. And then below that, there's a bunch of numbers, which is basically the telemetry blown out in blue here. And if you keep going down, you'll see red is the forecast. If you go up a little bit, there's an intersection. So I can't read that. I think it's like 1 p.m. It was 43 in the base area, and my forecast is 43, so that's pretty good. This I can't read. I think around 35 at mountaintop. You'll see in the middle there's no forecast. There's a couple sensors. There's this one. There's one at Alpental. If there's no good data coming from the sensors, you talked about noise before, it won't be able to produce a good forecast. In this case, in Green Valley, we have a bad temperature sensor, so I don't have a forecast for that sensor because the machine couldn't learn off of good data, and it makes a bunch of stuff. If you go to the top, you can click on this guy right here, and you can pick any of the areas it has. So if you go to Stevens, or whatever you want, or Baker. Someone likes Baker more than Stevens. So here's the, again, 12, 24, 48, 72-hour water amounts. And here's the forecast, 12, 24, 48, 72 forecasts. And there's some charting below that. There's some interactivity here, too, if you want to zoom on the charts. It's really just an interface to understand how people would interact with this, what's useful to the practitioner, whether it be professional or recreational. And it'll evolve over time for sure. Working with NOAC to understand how does this interface with their forecast, where does the human forecaster come in, because that's still definitely a large component of it. But the link should stay live. It should stay up at winterscience.com. So you can look at that this winter, and really happy to get feedback of what you think of it, what you think of the accuracy. And if you click the next tab too, I want to real quick look at this. I don't know if you guys have run Snowpack. The next step you can take with this, you can take all this model output, you can combine it with the weather station data, you can actually get a model of what the Snowpack is. It's made by the Swiss, and it's something I hope to have up in 30 days or so. You should be able to look at every data logger that NOAC has and get a Snowpack model based off that data logger updated in real time. So if you scroll across this timeline on the left, this is looking at last year at Crystal. Oh, something happened. It's a little complicated to look at the first time you see it. This green here is new snow. This is time. And on the right, you're looking at a point in time. What does a snowpack look like? And at least there with the hardness layers, what's going on there? There's like a crust that shows up if you go to the right. Like right here, there's temperature. It gives you every variable you can imagine at every step through the snowpack. So you can take all this weather model data, dump it into snowpack model, and it will actually tell you what the snowpack looks like today or even 3 days in the future if you're running off of forecasted data at any point in the Cascades. Now, there's probably concerns about accuracy. I have concerns about how much you want to give out just to public, like how much leverage do they put on these snow pits. There's even like it gives you shear strength and general stability ratings in some of here, and there's a lot of, I think, discussion needs to happen of, well, how much how much you directly put out in front of a recreational or professional user that you feel good about them understanding what it is. But I do think it's something that we should keep pushing towards and understand how those interfaces work, because the technology is available there today to do it. And it's right now sitting a lot in universities and research, and a few places in Europe are doing it, but there's not really the practical component. I want people to see the usability of this stuff. That's about all I have. Weather, Snowpack, website, more to come.
We'll stay up here for some questions. Yep. I'm sure somebody has a question for Chris.
Any questions? Yeah.
Right there.
Actually, I have two questions. The first is, what is the grid size?
Yes, I glossed over a lot of technical details. The grid size is 3 by 3 kilometers, meaning there's a point every 3 by 3 kilometers across Washington State on my nested grid, and then there's 37 or 40 elevation layers.
And then for your temperature verifications, how far out was that WRF output?
How far out does it go? So I hacked those together last night. It was actually, if you looked at that chart, it went back probably about 24 hours. Okay. So there's multiple forecasts actually in that chart. So you're looking at 24 to 48 hours of a forecast, future. But the question really is how far out can you accurately forecast those temperatures? One of the benefits of doing this is you can continuously update the forecast all day, but again, there's some risk with that of can people deal with continually changing variables on the page? Because I say a quarter, and I say a half, and I say 4/10. It depends when you look at it.
Thanks.
How about another question? Oh, thank you for coming up to use the microphone.
You're welcome. Is it on? It's not even on, is it? Okay. So I, like you, work in a field in which everyone is skeptical of machine learning. I'm an ecologist. And so one of the things I found most valuable is most people are skeptical of these kinds of techniques because of their lack of robustness in terms of novel situations. So like, maybe a novel weather system that hasn't been observed by the sensors that you have. Learning on something that hasn't occurred is difficult. So one of the things that I think has been interesting is, in my own work, is creating simulated examples, training the system on simulated examples, and then seeing how robust they are in terms of creating new novel examples and whether or not they, present any sort of accuracy in those situations. Have you thought about like simulating these things to prove their robustness in a more rigorous way, or have you just been sort of using real data?
Yeah, the root of the problem is the machine can't learn off something it's never seen before. You usually see it in this case like big precipitation amounts. Right? It hasn't seen 6 inches of water in 24 hours at like Mount Hood that many times, so it's hard for it to forecast that event. Some of that I focus less on because those are so well forecasted anyways, where it's 4, 6, or 8 inches of water. It's going to be a huge water amount. In terms of like forcing it to learn historically, I pull in historical GFS runs, and I run the model historically for past years. I need to match that up with weather data to do that. It'd be really hard to create complete simulations without that, so I really need the NOAC weather stations to tell me what happened. Mm-hmm. And their data only goes back to 2014 in their database. So that's it's a limitation of how far I can go back. I have enough data to do it. I have maybe 15,000 hours I can learn off of, but I don't. I probably won't spend a ton of time forcing it into unique situations. It's a different bent trying to like forecast, low elevation snowfall or something like that. It's a good point though. It's a limitation. You can't forecast very rare events very well, but I find that those are usually forecasted pretty well. Yeah. Unlike that wind event we had a week ago, but my model killed it because it like under forecasted everything, right? Because it's never seen that before. So I was like, I'm going to be like 30 miles an hour, and it was 30 miles an hour. So I nailed it.
Awesome. Thank you so much, Chris.
Yeah.
Thank you, Chris.